Okay, so now we're going to talk about section 8.3. We're going to talk a little bit about radioactivity. Radioactivity is a phenomenon that was first observed at the beginning of the 20th century, end of the 19th and beginning of, so that would be like 1898, 1899, somewhere around there. When people were studying the chemistry and the energetics of atoms. So a lot of people were working on figuring out all of the different types of elements that are in nature. They wanted to fill out the periodic table completely. They wanted to see if there were any differences between atoms. And when they started applying a lot of the techniques that they had developed, what they found was that certain elements gave off particles, very light particles that could fly through space across the room. And if you had some photographic film on the other side of the room, it would light up the photographic film. And so they realized very quickly that these particles had a lot of energy to be able to fly across the room and expose film, right? The people that worked on it, many of them died because these radioactive materials, working with them day in and day out, were actually very dangerous to them. And so you've perhaps heard of Madame Curie. She was a very famous chemist who had worked on these radioactive materials. She died of cancer. Many of the people that worked on these materials died. So we learned a lot from the sacrifices of those individuals. So when we use the term radioactivity, what we mean, think of a circle. You know how a circle has a radius, meaning you start at the center and you move out to the circumference, right? The idea of radioactivity is that particles are starting off in the atom and then they're flying out into space in all directions. So if you go in all directions, you get a circle in 2 dimensions or a sphere in 3 dimensions. So radioactivity just means things are radiating outward from some source. Now we know a lot about radioactivity now. So what we're going to do is we're going to say the cause of it is that some atoms are just inherently unstable. And over time, they spontaneously decay into new atoms, okay? So for example, a uranium atom can spontaneously decay into a thorium atom, a different element in the periodic table. When that happens, a small particle, a light particle, light meaning not much weight, is radiated outside. Essentially what happens is the atom breaks apart and part of it will fly off into space. And that's what we call the radiation. When someone says you've been exposed to radiation, that's the particle that's been emitted from this atom, okay? Now there are, in general, there's more than 3, but in general, we'll focus on 3 different types of particles that can be emitted. The first one is called an alpha particle. Historically, it was the first one to be kind of studied. So we call it alpha for A. Alpha is the Greek letter A. It's a positively charged nucleus from helium. So if you take a helium nucleus, helium is element number 2. It has 2 protons. And then there's an isotope of helium that has 2 neutrons. So 2 protons and 2 neutrons. We call that helium-4. That's called an alpha particle. It's positively charged because it doesn't have any electrons in it when it escapes the atom. Now, the thing about alpha particles is that they can be stopped by other atoms before they travel too far. So even if you had a material producing alpha particles and you put a piece of paper next to it, the paper would actually absorb most of the alpha particles and would stop them from penetrating through. So alpha particles are generally not that dangerous unless you ingest them or you have an open wound. So if you drink something or eat something that has emitting alpha particles, then that can be very dangerous because you have soft tissue and there's really nothing to stop those particles from damaging that soft tissue. But outside, clothing will stop alpha particles, paper will stop alpha particles. The second type is called a beta, again, alpha beta, right? Beta is the second letter in the Greek alphabet. A beta particle is really just an electron. It's an electron that's formed from the decay of 1 neutron in the nucleus. So essentially the neutron in the nucleus is converted into an electron and a proton. Okay. The electron is very light and it takes a bunch of energy with it and just flies off into space. Okay, that's the radiation that we're talking about. So when we say something is radioactive, we means it gives off radiation. The radiation itself is the alpha or the beta, or as we'll see, the gamma particles. Now, beta particles can travel a little bit further than alpha particles. They can actually get through thin pieces of paper. Paper will stop them a little bit. Some of them will get stopped, but not all of them. But they generally don't go too far, a few inches to maybe a few feet before they get absorbed by other materials like air. Okay, 6 feet away, beta particles are not going to interact with you. You don't have to worry about them. The third type is maybe the most dangerous one in general. It's called the gamma ray or gamma particle. Again, it's alpha, beta, gamma, so that's the third letter in the Greek alphabet. It's a packet of energy. Unlike an alpha or beta, it doesn't have any mass. It's actually a photon. It's like the light that we see coming from a light bulb or the sun, but it's a very high energy type of particle or photon. It's a very high energy. It's millions of times more energy in one gamma photon than there is in visible light. So it's actually very dangerous. It doesn't have any electrical charge and it doesn't have any mass. So nothing really stops it. It just keeps on flying. Every once in a while, it will interact with an atom and wreak havoc on that atom. It can cause damage. And so it is capable of breaking chemical bonds. We are made up of chemicals, including DNA. So if you can break DNA, that could cause damage to cellular tissue. Very deeply penetrating. We use the term penetration here, that it can go through a lot of matter. And it can even go through lead and gold. You know, it's a very high energy particle. When we talk about radioactivity, where does it occur? Luckily for us, most elements or most atoms are pretty stable. They're not radioactive, only some are. So carbon-12, for example, which is what the carbon that we're made out of mostly, 99.9%, is very stable. And when we're looking at light elements like carbon or oxygen or nitrogen, or the ones that have fewer than 20 protons, those are the light elements. They're generally very stable if they have the same number of protons and neutrons. They're equal. So for example, carbon-12 is very stable. It has 6 protons and 6 neutrons. They're equal. Oxygen-16 is the most common form of oxygen in humans. It's also very stable, lasts billions of years. And oxygen-16 has 8 protons and 8 neutrons, so they're equal. But when you get into the heavier elements, more than 20 protons, so for example, iron has 26 protons, the atomic number is 26. You tend to need more neutrons to hold them together than you have protons. The protons, remember, are positively charged. They want to get away from each other. So the neutrons are holding the protons together. And there's a constant struggle. The protons trying to fly apart, the neutrons trying to hold them together. When you get up to the heavier elements, you need more neutrons to hold those protons, the larger number of protons together. So for example, iron 56, that's a pretty stable form of iron. It has 26 protons, but it has 30 neutrons, more neutrons than protons. So lighter elements, generally 1-to-1 ratio, heavier elements, a little more neutrons than you have protons. Okay, so let me show you a little picture here. Okay. The idea of like a uranium atom. This is the uranium nucleus. Again, we're not really worried about the electrons yet. We'll get to that when we start dealing with chemistry. So this is uranium. Uranium is element number 92. And there are different forms of it, but one form is 232. Oops, sorry, 232. Let me write that number again. You might remember the term top heavy. Generally, the number at the top is larger than the one at the bottom. Remember, this is the atomic number. And this is the mass number. Okay, neutrons plus protons, that's the total. Nucleons, we call them, right? And then this is the number of protons. Okay, so what we find is that you have a lot of positive charge in there, like 92 particles, 92 protons, all in there. That's a lot of protons, and they're all trying to fight away from each other. So what do we have? We have all these neutrons in there. Holding them together. But even so, even with that, when you get up to 92 protons, that's so many protons, it's just even the neutrons, even these large numbers of neutrons, really, over time, they can't hold the atom together. So over time, the uranium atom is going to decay away. So we can write, I'm going to show you example 8.1. What they do is they say they want you to find the symbol for the decay product when uranium goes through an alpha decay. So we're going to say that the uranium 232 will go through an alpha decay. So we're told that. That's not something we have to figure out. Write the symbols for the uranium, the alpha particle, and what we're going to call the daughter nucleus. The daughter nucleus is the product of the decay. Okay, so let me show you how you go about this. The first thing we know is this. This is given in the problem. We're told that. So I'm going to write that symbol first. Okay, that's the uranium-232. We're then told it goes through an alpha decay. So what I'm going to do is I'm going to write a little arrow. We'll see a lot of this in chemistry, writing these arrows. And that arrow tells us that we're going to get products. So these are called products. Okay. So you can almost think of it like in time. You start with uranium-232. Over time, you're going to get new things. So essentially what happens is this little uranium atom is just going to pop off a helium nucleus. It's going to pop off an alpha particle. Okay, and remember the alpha particle has 2 protons and 2 neutrons. Okay, now we use a very specific symbol for the alpha particle. It looks like this. You write He, and then 2 protons, and the mass number is 4. So that's an alpha. So if they say it undergoes an alpha decay, you write the symbol for helium, and then you write 2,4. Okay, so an alpha is 2,4. In fact, I'll write that over here. Okay, that's just the symbol that we use for the alpha. But now what we want to do is we want to find out what the other product is, what's called the daughter nucleus. Okay, the daughter nucleus is what's left behind after you lose the alpha, which is most of it. Almost everything's still there. We just lost 2 protons and 2 neutrons. So here's what you do. We'll assume that the number of protons on this side is equal to the number on this side. That's technically not correct. Really what we're doing is we're saying the electrical charge is the same on both sides. So the electrical charge is essentially the lower number, the atomic number. So if we have 92 on this side, we have to have 92 on this side. Well, 2 of the 92 are here, so that means we have to have 90 left over. Okay, So what I'm doing is I'm claiming these two numbers here, 92, have to equal this number here, 92. Okay. So if you're told it's an alpha decay, you know that it's a 2 for the helium. So you just figure out by using subtraction what the other one is. 92 minus 2 would be 90. Now, that's the atomic number. So we go to the periodic table and we look up what the atomic number, what the symbol is for that. And so I don't want to switch out of the screen, so I'm just going to go ahead and tell you, if you look at the periodic table, 90, oops, sorry, 90 goes up here, is called thorium, TH. So this is from the periodic table. Okay. So thorium, so you write the symbol TH for thorium. Okay. Now, just like we said that the charge has to be conserved, right? Remember these conservation rules we had? Conservation of energy, conservation of mass, conservation of momentum, conservation of angular momentum. Charge and mass have to be conserved. We can't create or destroy. So if we have 32 as the mass number here, we've got to have 232 over here. But 4 is over here. So again, you just use subtraction. 232 equals 4 plus some number. Well, x would just be 232 minus 4, which would be 228. So we would write that number up there. Okay. So this would be called thorium 228. Okay. And that would be the, the symbol, the isotopic symbol for the daughter nucleus. Okay. So the number on the bottom, that's the atomic number. Those have to add up on both sides. And then the mass number on the left has to equal the sum of the mass numbers on the right as well. Okay. Now, since that involves a few steps, what I'm going to do, sorry, just take me a minute. I just want to find another example for us to go through so that you can see this. Okay. So let me bring up another whiteboard here. Okay. So this is one from the end of the chapter, it's number 14. And it says the boron isotope, and then they say it's boron 512, okay, decays into the carbon isotope C612. What kind of particle is produced? Okay. So here they're actually telling you both what the starting material is, the starting nucleus, this radioactive, and they're also telling you the daughter nucleus, right, the product. So let me just very briefly here, right over here, we have our alpha particle. And remember, that's written as He24. The beta can be written in different ways, but one way is just to write an E with a -1 as the atomic number and 0 as the mass number. An electron does have mass, but it's so much smaller than a neutron or a proton that we essentially write the mass number as 0. And then you've also got a gamma. And the symbol for gamma looks like this, but it doesn't have any charge or mass. So the atomic number is 0 and the mass number is 0. Okay. So those are our three choices. Presumably those are our three choices. Let's see. Let's try this one. So we're going to start with boron 512. And then we're told that it goes into, it becomes 612. Now there's actually a couple of others. So let me just write this one. This is called a positron. Positron is an example of antimatter. It's also an electron, but it has a charge of +1. So it's actually +1 and then has a mass number of 0. So those are most likely your 4 options. I just want to make sure you get everything possible. Okay. So now that's your daughter nucleus. The daughter nucleus is going to have, the numbers are going to be pretty much the same, similar. Okay. Now, here's how we go about it. Let's do the atomic number first. Whatever we have on this side has to be equal to what we have on this side. So 5 has to equal 6 plus something. I'll write it as x. We don't know what it is. So let's figure out what it is. You subtract 6 from both sides. 5 minus 6 is -1, right? So that means it's got to be -1. Well, right there, we only have one that has -1 as an atomic number. That's the electron. So we know it's that one. We also know that the mass number of an electron is 0, but let's confirm that. The mass number should be the same on this side as it is on the other side, the right side. So 12 equals 12 plus, that's got to be a 0, right? 12 is equal to 12 plus 0. So that means this is a 0. So in fact, this is a beta particle. Okay. So in this case, we're not asked for the daughter nucleus, we're just asked for the particle that gets emitted. Okay. Let's see. Any others? Okay, let's maybe look at one more. Okay, this is number 17. I'm sorry, let's do number 18. Number 18 says a copper 2964 nucleus can decay by emitting an electron or a positron. Okay. And also, so there's actually 3, by capturing an electron. Okay. What is the final nucleus? In each case. So we're actually going to have 3 reactions. Each of them are going to start off with the copper 64. Okay. It can decay by emitting. That means it's producing an electron. Remember, the electron is -1, 0. It can also decay by producing a positron. The positron is the electron with a positive charge. And it can also do a third thing. Now, this one's a little bit different. Capturing means you're taking something. So it actually adds an electron. Remember, atoms have electrons, and it turns out sometimes some of these heavier elements can capture an electron, one of their own electrons. We'll get, we'll see more about electrons when we get to the chemistry, but this is called electron capture. Okay, so let's go through them one by one. Let's do the charges first. 29 is equal to -1 plus something. Okay, well, that would be 30. -1 plus 30 is equal to 29, right? So that's got to be a 30 there. 64 equals 0 plus 64, right? Hopefully that makes sense. So what we have to do then is we have to figure out what element number 30 is. So if you go to your periodic table, what you'll find is that number 30 is zinc. Okay, so that's zinc. I just got that from the periodic table. Right, because element number 30 is the atomic number. And that would be zinc. Okay, let's try the second one. 29 equals 1 plus 28. Right, 28 plus 1 is 29. So that's the bottom. Let's do the top. 64 equals 0 plus 64. Right. So then we go to the periodic table. We look up number 28, and that turns out to be nickel. Right. Nickel is element number 28. Again, you go to the periodic table. Okay, so if it says electron capture, though, it's a little bit different. We put it on the reactant side, on the left side. So 28 plus a minus 1 is, I'm sorry, 29 plus a minus 1 is 28. And again, 28 is nickel. And then 64 plus 0 is 64. So notice there's actually two different ways to get the same isotope of nickel, either through emitting a beta particle, an electron, or by capturing an electron from the atom itself. That's called electron capture. Both of those give you nickel. And then there's a third mechanism where you actually emit an electron, and that one right there is going to produce zinc. Okay. So again, you've got your alpha. Alpha is written as He24. You got your beta, and that's written as E minus 10. You got your positron, which is E plus 10. And then electron capture, that's on the same side. Okay, again, it's just an electron, but you put it on the left side. Okay, the electron capture, the electrons on the left side. Okay, so hopefully that will help you with doing some of the homework problems. This is really the first section where we can do a lot of calculations, using this. Again, these are isotopic notation, right? But now we have these really 4 different particles that can be released in the process: alpha, beta, gamma, and then positron. Okay.